কাজলদা,
হ্যাঁ
কাজল আমি একবার চেক করে নেবো এটা আছে কিনা।
আচ্ছা, চেক করো। হ্যাঁ 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 আসছে।
আচ্ছা, স্লাইড গুলো চেঞ্জ হচ্ছে কিনা একটু দেখে নিন না। দেখা যাচ্ছে কিছু
হ্যাঁ 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 দেখা যাচ্ছে।
অ্যানিমেশন দেখা যাচ্ছে এইগুলো।
হ্যাঁ স্লাইড দেখা যাচ্ছে।
আচ্ছা ঠিক আছে ঠিক আছে। আর এই চেঞ্জ গুলো দেখা যাচ্ছে, অ্যানিমেশনের
হ্যাঁ হ্যাঁ
চেঞ্জ
চেঞ্জ
গুলো।
গুলো দেখা যাচ্ছে, অ্যানিমেশন গুলো আসছে।
আচ্ছা তাহলে ঠিক আছে।
অর্ণব আছো নাকি তুমি? অনলাইন আছো? আচ্ছা গোলাম, তাহলে কি আমি শুরু করি নাকি?
শুরু করে দেয়।
Hello everyone. Good Good evening to you all. On behalf of our college, BB College, I welcome you here. We have arranged on behalf of the PG Department of Physics. We have today arranged a seminar talk to be delivered by Dr. Golam Ali Sheikh on the topic of S.N. Bose and his statistical approach in the development of modern physics. Before that, uh, I give a brief introduction of Dr. Golam Ali Sheikh. Presently, he is in the position of assistant professor in the Department of Physics, Kazi Nazrul University. Earlier, he also worked in our Department of Physics of BB College, Asansol. And before that, he was assistant professor in the post of assistant professor at the Kashmir University, the Department of Physics. And though I do not know about him in detail, but I can say that he did his postdoctoral research in Italy and Serbia. I think, if I am right, he did it for 3 long years, I think. And he has published more than 30 publications, 30 articles he has published in different reputed journals. So here's the brief introduction of Dr. Golam Ali Sheikh. And let us welcome him to deliver today's lecture on S.N. Bose and his statistical approach and the development of modern physics.
Okay. So good afternoon, good evening, everybody. So first of all, I would like to thank Dr. Kajal Krishnadev for introducing me. I would like to thank the BB College and the Department of Physics, PG Department of Physics, for giving me the opportunity to talk on the topic. So let me start, and the topic actually it's better not to delay. So let me share. So can
you
you
can
share?
start.
Okay, so let me start. So is it visible? Just let me know, Kajal.
It is clearly visible.
Okay, okay. So basically, my today I would like to talk on the SN Bose and his statistical approach. And more or less, we physics student, everybody knows about this SN Bose. So so let me first introduce what was his basically contribution. How do we come? How it becomes so important, and about a little bit about his life also. So so what was the major problem? I mean, in the physics, what was the major problem in the 19th century? There are basically two major problems. So one is that how light travels without ether. I mean, without any medium. Uh, because the light comes from sun and there is no medium. So how it comes? And the second problem is that how there was no sufficient adequate theory, that is to explain blackbody radiation. So so what was the problem actually? So basically the blackbody spectrum, it's a continuous spectrum. But at that time there was no theory to explain that. So once I mean, there was a theory that is called Rayleigh-Jean's law, which can explain only the I mean, higher wavelength region. In the short wavelength region, it is not possible. So then the Planck's radiation formula comes. So, but it's based on exactly the mixture of classical and quantum concept. And then it resolved the issues. But still the problem was remain. I mean, the people are searching, is there any other way to resolve the problem? So, so let me introduce what was the basically the major discoveries in 20th century. So The thing is that there was a Planck theory of blackbody spectra which come in 2000, in 1919, and then we have relativistic theory. Then we have the photoelectric effect. Then we got the superconductivity. Then Bohr atomic model. Then general theory of relativity. Then we have the Compton effect. Then de Broglie, and finally we got the quantum statistics in 1924. So this is actually the relativity and relativistic the physics which we study as a combination of relativity and quantum physics is called basically the modern physics. What we know, the modern physics is the combination of relativity and the uh, quantum mechanics, and that is why I call it in the development modern physics. So now, what is the before going to the detail of this all kinds of details? So let me just let us try to try to know about the man behind this quantum statistics. So we know the SN Bose has I mean he born in 1894, and then of course he studied in Hindu college, and then after he went Presidency College, and from there he went to Calcutta University. And after that, he joined as a Dhaka University. So while working in Dhaka University, he has some concept. I mean, she has some idea how to derive this. Is there any other way to derive the Planck radiation formula? So he was thinking. Now suddenly, a thing suddenly actually he was to the best of my knowledge he was teaching something like that some let us go geometrical that is called progression like this. So he was thinking, is it possible? At that time, actually, we have already understood that at that time the Planck radiation formula already come into the picture. So Planck's uh, that is the when the light travel or when it is absorbed by black body or somebody or it emitted as a quantum of radiation. So that means the photon concept had already come into the picture. So now he think, is it possible to consider the radiation as a particles, and is it possible to find the distribution of the particle? So exactly he did it, and he considered that there are several number of let's say boxes and the photons, that is the called the number of, that is the photon, that is the particle, you can say the particle, indistinguishable particle, they can be distributed in the different cells or different boxes, and from that he derived a distribution formula that is called the Bose, which we call the Bose distribution. But what is the importance here? The importance is that he in the previous calculation, what they have done, they have considered the classical concept, that is what are the number of modes in the frequency range nu 2 nu plus something nu 2 nu plus d nu. But here he considered only the phase space concept. Like he only considered the case that is the minimum volume occupied by a photon is hq HQ, that is the Planck constant, the minimum. So that concept he only used in his derivation, and finally he got the formula. So basically, the main contribution is that if you I mean, so what he pointed in his paper, that he has derived this factor without taking recourse any kind of classical concept, just use the concept of HQ. And finally, of course, this is the Blackbody radiation formula. That is, we know this and the spectrum, and using this formula. I mean, this is same with the Planck radiation formula. So he derived it in a different way. And after the derivation, what he did. So basically, what he did, basically he considered the. Let me repeat it once again. So he considered that the bosons are these photons are that is the quantum of light are distributing in different cell, and they are indistinguishable, and the total energy is conserved, and from that concept he derived the Planck's radiation formula. Okay. And after the derivation, normally what we do, we normally the science people, what I mean the who are doing research, what we do normally, we normally if you have some concept, we write the concept and we work out on the concept, and then we send it to the some journals, and there is some reviewers, so reviewers see the paper, and then if it is let's say they think that is correct, they publish the paper. So the Sutton Bose has done the same thing. I mean, he has published sent the paper to some magazine, that is journal, philosophical magazine. But unfortunately, the referees, I mean, they could not understand the importance of the paper. So of course, if somebody doesn't understand, so they definitely they rejected that. They have thought that this is just nuisance. Nothing is new here. So they have rejected the paper. And what Washington Bose did, so while rejecting the paper, so he was just write a letter to the Einstein. So he asked him to publish the paper if he think that the paper has some importance. I mean, the work has some importance. Then he asked the Einstein. I asked Einstein to publish his work in some journal. In and he also requested him to translate it in German language and publish in some German journals. So Einstein was immediately understand the importance of the work. Of course, it has some importance, so he realized, and he put a note there that Bose's derivation appears to me an important step forward. The method used here also yield the quantum theory of an ideal gas, as I shall show elsewhere. So, writing this note, what he did, he just translate his paper into German language and submit it to Sanskrit for Physica. So, and the paper, of course, Einstein sent the paper, so of course this paper has published there. Now, after that, what Einstein did? Einstein in the Bose statistics. So the statistics was what was done by what was derived by the Bose is the statistics for photon. And we all know that photon has no mass. So of course, the constant of mass was not there. Only the constraint that Bose used was the constant of energy. That is the total energy is constant. So what Einstein did, he used this concept to the material particle. That is where the number of atoms or particles are conserved, in addition to the energy conservation. And he got a formula, a statistics which is presently known as the Bose-Einstein statistics. So basically, it is done in 1924. So if you can see here, I have written some formula, that is how the number of particles are distributed in some energy state, that is epsilon n epsilon. So n epsilon is the average number of particle in some energy state epsilon. So you can see the picture. You can see from the picture is that there is some at some situation you have a state can have uh, infinite number of occupation, because there is no. I mean, this is the parallel line basically. So there is a state can accommodate any number of particles, because it has no limitation. So there could be some situation. So when the situation arises and how it could be done, that is basically called Bose-Einstein condensation. So I will go to the detail of the Bose-Einstein condensation. So that means this is the concept where you can see that okay, a state can have the infinite number of occupancy. So a state can accommodate any number of atoms. But how could it be possible? A state because if you let's say cool a system. So suppose you have a system with room temperature. That means the atoms, you can see the atoms are distributed. So this is, let's say this is the system, because here I draw some trapping, because in the ideal case you can have the free atom, but in reality you need something to keep the atoms, I mean to hold the atom. So here is the trap, and the atoms in normal temperature, atoms should be distributed in different cells. I mean, normally what happened, the in room temperature, it has a more number of energy, the atoms has more energy, so that they should try to occupy in the highest energy state. So the atoms are distributing. That there are few atoms in the low energy state, and the number of atoms will increase with the energy as we go to the higher energy state. So this is very obvious because you room temperature the atoms should have more energy, so they should occupy in the higher energy state. Now what you do? You just decrease the temperature. So what will happen if you decrease the temperature? So basically you see that the number should, I mean, if you decrease the temperature, then the atom which are occupying in the higher energy state, what will happen? These atom don't have the energy to stay in that state. So they should come to the lower, relatively lower state. Now, if you decrease more temperature, then these atom also they don't have that energy to stay in that state. So they will come to the lower state. And in that way, all the atom should gather in the lowest energy state at absolutely zero, I mean nearly absolute zero temperature. So that means that the concept is that the Bose's concept was the, I mean the Einstein concept was that the statistics says that a state can occupy in principle any number of atoms. So in that time it is I should say that in that time there is no concept of boson, photon, and other, I mean boson and fermion. So that is the only situation, only phenomena people are expecting. Is it possible in reality that kind of phenomenon is available? I mean it could be achievable, or it is possible in nature. So that was the let's say some kind of uh, I mean how could it be possible? Because there is who and which atom would follow this kind of things. So there is no nothing actually, not such kind of concept. But which atom they behave like this? So after that, of course, the Fermi statistics come. So I'm not going to the detail of that. And then at that time, I mean, you see that almost the classification comes into the picture. Now let's go to the more physical changes of the atom. How atoms are, I mean, what kind of physical changes and quantum mechanically the atom is facing. So in that case, you can say at the room temperature, what happened? The atoms have more energy. That means they are de Broglie wavelength, which we know that it is the inversely proportional to the temperature of the atom. So as the temperature is high, that means they have very less. Let's say the de Broglie wavelength is size of the de Broglie wavelength is very small. So that means they have very less overlap. So that means and at high temperature, what happened? The de Broglie wavelength, the length of the, I mean, size of the de Broglie wavelength almost equal to the dimension of the atom. So there is no role of I mean the classical quantum mechanical constant does not come into the picture. So they behave like a classical billiard ball. Now as you decrease the temperature, what happened? The of course the wavelength will increase because it is inverse. The wavelength is inversely proportional to the temperature. So of course the de Broglie wavelength will also increase. But still they are not behaving like a just like a classical, but they have no quantum mechanical concept does not come. So if you decrease more and more temperature, then you will see that the wavelength will increase, and finally this wavelength will overlap. And at absolute zero temperature or nearly absolute zero temperature, what happens? All the wavelengths overlaps and they forms a giant wave. So that is basically we call as Bose-Einstein. So you can see that how the this physical changes occurring when you go from high temperature to lower temperature. Okay. So this is the actually the theoretical point. Now, how could it be possible in the laboratory? So is it possible in the laboratory? As you can see that the BEC was predicted in 1924, of course by Einstein. But the thing is that it is only observed in 1995. So it almost takes 70 years to observe the bees in the laboratory. So what was the problem basically? The problem is that the cooling technique. Sorry. The problem was the cooling technique. So it takes a lot of lot of time uh, to let's say to find some technique to cool the atom in such a low temperature. So So basically I'm not going to the all detail of the cooling technique, but I will give some less I mean some idea of the cooling. So what happened, you know that the temperature depends only on the kinetic energy. So somehow if you decrease the kinetic energy of an atom or of any particle, so its temperature should decrease. So this can be done by the by using some laser. So we call it the laser cooling. So laser cooling has several that is Doppler cooling and other things. So I'm calling just using just laser cooling. So what normally you do, so suppose you have you have atom in the trap, so you apply some laser from one side. So what happen, from the laser, photon will absorb to the atom. So atom will get some kick, that means some change, momentum change will occur. And due to the momentum change, the atom should, the kinetic energy of the atom should decrease. Of course, this atom will re-emit. So the re-emission should be random and spontaneous emission, and as a result, there should be no changes of the atom. So basically, no changes of kinetic energy. So only the change while it hit the atom. And so as a result, what happened? This atom's kinetic energies will decrease, and the temperature definitely decreases. And there are more detail of the laser cooling, Doppler cooling. So I'm not going all the details. So now, but the using laser cooling, what happened, or Doppler cooling, the temperature cannot be decreased more than 100 100 about 100 microkelvin, but 100 microkelvin is not sufficient, or around 100 microkelvin is not sufficient to observe peace in the laboratory. So we need something which is very close to the absolute zero temperature. So how could it be possible? So then there are several techniques. So one of the technique is that is called the evaporative cooling technique. So what happened in the evaporative cooling technique? We all know about the evaporative cooling technique. So like when you have a tea in a pot, so I mean cup. So what happened? So your the hottest particle in the on the top of your uh, teacup, they they evaporate. I mean they just uh, escape from the teapot, and as a result, what happened? I mean, the hottest particle leave the pot, and as a result, the whole uh, 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 tea get rethermalized. And as a result, what happened? The average energy of the teapot, I mean tea, should decrease. So this is what happened here. So there are two ways you can do it. So what you have do, you have a trap. So the atoms are in the trap. So you just slowly decrease the trap, and once you decrease the height of the trap, you can see the most energetic atom will leave the trap, and as a result, the number of course, as a result, the average energy of the atom should decrease. But here you should see that there is some limitation, because once you decrease the number of atoms, that means once you decrease the size of the trap, the number of atoms should decrease. So but you need some kind of, let's say, some limit, some critical number of atoms to observe BSC. So that will decrease the number of atoms. So there are another way, that is called spin flopping. So they can use the spin flopping technique to reduce the number, I mean to take the high energetic atom from the trap. So, but this is basically called the evaporative cooling technique. So, using the evaporative cooling technique and the laser cooling technique, it is possible to observe Bose-Einstein condensation in the laboratory. So, so this is the typical picture of the Bose-Einstein condensation, which is observed in the first experiment. So here you can see the blue part basically gives the condensed part, and the green part, yellow part is the just thermal cloud. So you can see that as the temperature decreases from 200 nanokelvin to 0 nanokelvin, you can see the green part increases, and the thermal part, that is the red and yellow part, decreases. So this is the basically the significance of the BEC. Okay, so there is another way that what they do. So this is called the measurement is done by time of flight method. So basically once the BSC form, they just remove the trap, and they see how the cloud is expanding. From there, so basically they study. So if there is some anisotropic expanding. So if there is no condensation, this will isotropic expanding. That means they are expanding in a isotropic way. But if there is condensation, there is anisotropic expanding. So this is another signature of, and there is the atoms are in the BAC. This is the interaction. So in that case, in this context, I want to say that you know that in the ideal BAC there is no role of interaction, but basically in the reality, uh, you have the interaction between the atoms. So this interaction definitely uh, should be there in the system. And more specifically, this interaction can also be controlled using the in the BEC, and this is the flexibility of the BEC, that you can control the even the this interaction of atomic interaction using some artificial way. So this is there is another flexibility of Bose-Einstein condensation. So now for this achievement in 2000, and this technique is called basically the phase break resonance technique. Now, for this achievement in 2001, two groups. So one from the University of Colorado at Boulder, that is Eric Cornell and women, they got the Nobel Prize, and also another group, that is MIT group. Uh, Catterley also get the Nobel Prize for that. So basically, these two groups discovered this condensation almost simultaneously. One group for rubidium atom and Catterley group for sodium atoms. Okay. So now, what is the my conclusion? Conclusion is that what should be the advantage of creating Bose-Einstein condensation? So of course, it's the verification of the basic phenomena. I mean, this physical phenomena, that is one of the curiosity of the physicists, that how to verify, how to check the all the existing phenomena. So this is the interesting. I mean, this is the way, one of the greatest achievement that allow us to experimentally verify the existence of quantum particles. So this is one of the great achievement. But uh, what we are doing right now actually. So this is now, at the time, the BC is becomes a fascinating tool for simulating different physical system, including its ranges from quantum matter to nonlinear science, and also in quantum computation. So, what we're doing, where some people are there, a lot of works is going on the Anderson delocalization system, Josephson oscillation, and BC in optical lattice also gives you the idea of about the some standard quantum matter system, where you have a lattice actually, so you can study the Mott insulator, and you can study the band structure. But here only the importance is that you can even control the let's say the band gap, and other that lattice spacing you can change using different kind of lattice that you want to, different kind of optical lattices, that is artificial periodic potential that in create in the system. And you can also study different kind of standard quantum meter system. And also there are also the experiment on soliton formation, that is a nonlinear property of the Bose-Einstein condensation. And also there are some other lot of experimental work is going on the using this Bose-Einstein condensation. So now what are the future prospect? I mean, what are the possible prospect? This is all the experiment and all the works in the BC basically all are in the primary stage. They are all just trying to create more and more stable BC. But there are some possible application. So one is that how it can be used as a quantum information processing, like quantum computation. It can be used as a coherent atomic beam. I mean, it is a very highly coherent atomic beam. So definitely it has application in atomic laser. It can be used as a precision measurement, that is quantum metrology, that people are using. And basically, I mean, there are possible way of detecting gravitational wave using BEC actually. So this work is going on. People are working on that. With that, I would like to thank everybody for attending my talk, and thank you, everybody.
Thank you, Dr.
Okay, I should also expect some questions from the students if they want to.
The session is
No.
now open for questioning. If you have any questions from students, it would be encouraging. স্টুডেন্টরা তোমরা যারা আছো তোমরা জিজ্ঞাসা করতে পারো যদি কোনো কোশ্চেন থাকে। উইদাউট এনি হেজিটেশন ইউ ক্যান আস্ক।
হ্যাঁ, বাংলায় জিজ্ঞেস করতে পার, কি আছে, অসুবিধা কিচ্ছু নেই।
হ্যালো, হ্যালো, বলো।
হ্যাঁ
হ্যালো, হ্যাঁ বলো বলো। হ্যালো,
হ্যাঁ 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 জিজ্ঞেস।
কোনো কোশ্চেন নেই? আই থিংক দেয়ার কোশ্চেন।
আচ্ছা, আমার মনে হয় স্টুডেন্ট খুব সহজ, একটু সবাই জানে হয়তো। হ্যাঁ, কাজল দা প্লিজ।
So thank you,
হ্যাঁ, থ্যাংক ইউ।
Golam. And I should mention here that I forget to mention that Dr. Golam Ali Sekh keeps interest in this field of research. You know, he keeps interest in ultra cold atoms and Bose-Einstein condensers. He's engaged in research in this field. And in future, if you have, I'm telling the students actually, if you have any question, if you have any query, you can ask him.
ইয়েস ইয়েস প্লিজ, অবশ্যই জিজ্ঞেস করবো যদি কোনো সমস্যা থাকে, কিছু থাকে, যে কোনো ভাবে, ফোন, টেলিফোন, মেল।
So I truly acknowledge you for delivering this lecture on
Thank you,
Einstein
Kajal.
Bose and his work from his childhood. And this lecture covered areas of work of Einstein Bose, from starting from his famous statistics and its application, you know, in the material particles, which led to the groundbreaking phenomenon known as Bose-Einstein condensation, its experimental exploration. So I once again thank you for such elaborating presentation. And I also like to express my sincere thanks to all the teachers who are present in this seminar, and also the students for your kind attention. So thank you once again all. And I think
হ্যাঁ,
we come to end.
থ্যাংক ইউ কাজল, থ্যাংক ইউ।
Okay, thank you all. So here we come to the end of this session.
কাজল দা, রেকর্ডিং বন্ধ করে দেবো?
হ্যাঁ হ্যাঁ হ্যাঁ,
ঠিক আছে, থ্যাংক ইউ গোলাম স্যার।
থ্যাংক ইউ।